Okay, and Bernoulli's equation can be applied to this situation here where you have a pipe going along like this, a drop in altitude. The altitude over here from here to here, y1, from here to here, y2. If you look at a cross-sectional area over here, the velocity through there, v1, the velocity through another cross-sectional area over here, v2. And if you consider the pressure of the fluid up here, that would be P1, and the pressure in the fluid down here, that would be P2. And it turns out that Bernoulli's equation states if you take the pressure at point 1 and add this expression, 1/2 times the density of the fluid times the velocity over there at point 1 squared plus the density times g times the altitude h1, well, that would be equal to the pressure at the second point plus 1/2 rho v2 squared plus rho g h2. This looks a little bit like a conservation of energy equation. You can recognize that the 1/2 mv squared, the kinetic energy, is similar to this term here, and the gravitational potential energy, mgh, for the fluid is associated with the rho gh. And the difference in the two pressures, that's kind of like the external work done. Let's apply this to an example problem. You see these water tanks throughout, the land. You see them from town to town, and basically here we have this water tank, and basically up here it has an open vent, and coming around down here, and the pipe goes over here to this person's house, and inside the person's house at that altitude you have the faucet. Now, they tell you here that the height to the base of this big tank is 15 meters. And they tell you that this big reservoir up here of water contains 5.25 times 10 to the 5th kilograms of water. And there's a couple questions here. Number one, what's the pressure down here? By this water faucet when the faucet is closed. And then part two, if the faucet is opened and they give you the radius of the little opening, how fast does the water end up coming out? So let's take this problem on. So the first thing we're going to have to do is figure out how high the water is over here. From here to the ground. We need to know this big height right here. We know from here to here, 15 meters. So if we want to get this big height all the way up top, we need to know this height right here. And in order to get that, if we knew the radius of this circular, spherical tank up here, we can multiply by 2 to get this additional height here. I'll call h prime. Now, the fact that they gave us the mass of that water up there will help us get the radius, will help us get the diameter, or the additional height, and if we add that to 15, we'll get the total height. So that's going to be job 1. Ready? Let's rock and roll. We know that density is equal to mass divided by volume, so 1,000 kilogram per meter cubed is going to equal to 5.25 times 10 to the 5th kilograms, and that's going to be divided by big V for the volume. And if I solve that for the volume, I get 525 cubic meters of water. Now, I know the volume of a sphere is 4/3 pi r cubed. So the 525 meters cubed equals 4/3 times 3.14 times r cubed. And if I solve that for r comes out to be about 5 meters. To take the cube root, I use the little exponent button to the 1/3. I know some calculators have a cube root button. I couldn't find it, so I just did it that way. So if I know the radius of that sphere up top, basically I can come back over here, and if that radius right here is 5 meters, then I know this additional height right here is 10 meters. And if I add that to the 15 meters, I know that this here is going to be 25 meters. Now, knowing that this point over here, I can call that point 1, is 25 meters off the ground, and I can find the pressure down here, and I'll call that point 2, and that's using that pressure depth formula. So basically, I know that P2 equals P1 plus rho GH. So the pressure down at the bottom equals the pressure up at top. And since they said it's an open vent, that's going to be atmospheric pressure, 10 to the 5th Pascal. And that's due to the open vent. Plus rho, 1,000 kilogram meters cubed. Kilogram per meter cubed times 10 meter per second squared times that height value of 25 meters. P2 equals, and that gives us pascals. And that's absolute pressure. If you wanted to get the gauge pressure, just subtract atmospheric pressure, and you would have -1 there. You'd have 250,000 pascals. And that brings us back to the second part, which was, so how fast does the water come out of this faucet? Well, first of all, if the pressure here is 350,000 pascals, and you come across right here to the same exact depth, then the pressure here, right on that faucet there, would also be 350,000 pascals. same depth. That's why they build those big towers, to keep the water pressure in all of our houses. All right, second part of the problem, how fast does that water come out of the faucet? They give you the radius of the opening, but it turns out that the velocity of the water coming out of the faucet does not depend on that radius, as we'll find out when we apply the Bernoulli equation. And basically, our 2 points are going to be this top point over here, and right down here where it comes out, 2, which is we're gonna consider at the same altitude down here. But here's the tricky thing. You know how we found this pressure right here? That was when the faucet was closed. But as soon as you open a faucet up, the pressure at the end right there is atmospheric pressure, because the only thing holding that fluid out, like the water, is the atmosphere would be pushing up against it. And way back here, since this is an open tank right there, open to the atmosphere, the pressure up there is also atmospheric pressure. So very odd, but basically both up here at the top, the pressure is going to be atmospheric pressure, and basically right there at the faucet, once you open it up, that's also going to be atmospheric pressure. And since both of them are the same on both sides, they're basically going to cancel out. Here's another thing. You see this velocity? That velocity corresponds to the velocity of the fluid up here. Well, when you run your faucet over here, there's going to be a serious velocity of the water coming out here, yes? But when that water comes out here, the water level here is going to be going down so slow that the water velocity dropping down here is going to be practically zero. So when we come over here, this term here also drops out because the water at the top of the tank is moving down so slowly. But we do have a substantial term here, the rho GH. So basically we have the density of the water, 1,000 kilograms per meter cubed, times G, 10 meters per second squared, times H. And what is that? That's the 25 meters. Now on the right-hand side, we could say that the height there is going to be 0 because it's basically down on the ground. So that's going to be equal to 1/2 times the density, 1,000 kilogram meter cubed, times that velocity there by the faucet squared. And if you solve for the velocity of the water coming out of the faucet, you get roughly 22 meters per second. Now, they gave you the radius in the problem. Knowing that radius, you can find the cross-sectional area. And knowing the cross-sectional area, you can use the equation of continuity and find the volume flow rate where the water comes out. How many cubic meters per second? Okay, folks, that's a wrap. Fluids out.